look around you right now. The lights above your head, the screen you're staring at, the cars rolling by outside your window. What is the foundational science powering all of that? I mean, the manufacturing, the transportation, literally everything we rely on every single day. Well, today on The Explainer, we are going to explore the invisible rulebook that dictates exactly how our modern world actually operates. Because here's the reality. Without energy, our global economy would quite literally come to a screeching halt. It forms the absolute backbone of all technological and engineering developments, period. So we're going to frame this explainer around the ultimate engineering objective, the real game we're all trying to win here, which is figuring out how to identify, harness, and efficiently transform energy into usable forms. So welcome to this explainer. Today, we're breaking down the universal rules of energy, straight from a university engineering syllabus. We are diving deep into the fundamentals of thermodynamics. You can really just think of this as the ultimate rulebook of reality. And here is how we're going to break it all down. First, the science of energy. 2, dimensions and units. 3, defining the system. 4, properties and states. And finally, 5, types of processes. All right, let's jump right into part 1, the science of energy. To really grasp the game we're playing here, let's just look at the word itself. Thermodynamics comes straight from the Greek, thermi for heat and dynamis for power. It's the science of energy, specifically how it's stored, how it transforms through heat and work, and crucially, the ultimate law of conservation, meaning energy simply cannot be created or destroyed. It can only be transformed. Picture this, classic physics analogy. You've got a rock resting on the edge of a cliff. Right now, it has, say, 10 units of potential energy and 0 kinetic energy. But as it falls, that potential energy smoothly shifts into kinetic energy. Mid-air, it drops to maybe 7 units of potential and 3 of kinetic. The total energy is still exactly 10 units. It's just wearing a different disguise. And the cool part is, this basic principle seamlessly scales up to massive engineering marvels. Think about a continuous cycle, a boiler taking in heat, a turbine cranking out work, a condenser releasing the excess heat, and a pump taking work in just to keep the whole cycle going. This loop is exactly how we transform raw heat into the usable mechanical work that powers entire cities. Which brings us to section 2, dimensions and units. Now, to play this game of energy, we obviously need a rigorous way to keep score, right? This means we have to characterize physical quantities precisely. We do this using 7 primary dimensions and their standard SI units, things like length in meters, mass in kilograms, or temperature in Kelvin. Every single physical quantity in engineering stems from these. Secondary dimensions, like velocity, volume, and energy itself, are literally just built mathematically by combining these 7 primary building blocks. Moving on to section 3, defining the system. So now that we know the rules, where is the game actually played? Well, when engineers tackle a really complex problem, the first thing they do is draw a clear line in the sand. They strictly define a specific region of matter for study, and they call that the system. Everything outside of that, that's the surroundings. And the boundary separating them is absolutely crucial for tracking what energy is actually going in and out. Now, that boundary can be a real physical surface, like a pipe wall, or a completely imaginary geometric surface. And these systems, they basically come in 3 main flavors. Honestly, the easiest way to ground this academic jargon is with a simple cup of coffee. First, you have an open system, also called a control volume. This allows both mass and energy to cross its boundary. Think of a regular open cup of hot coffee. Steam escapes and heat radiates away. Second, a closed system, or control mass. Here, only energy can cross the boundary, not mass. Picture that same coffee cup, but now you've popped a really tight lid on it. The liquid stays in, but the heat still escapes, so it gets cold. Finally, an isolated system. Neither mass nor energy can escape. Think of pouring that hot coffee into a tightly sealed, perfectly insulated thermos. All right, section 4, properties and states. Once we have our system clearly defined, we need to know its current stats. We do this through 2 different categories of properties. First, intensive properties. These are completely independent of mass. Whether you have a tiny little drop of boiling water or a massive industrial vat of it, the temperature is still exactly 100 degrees Celsius, right? But extensive properties are different. They scale directly alongside the mass. Double the amount of water, and you double its volume and its total energy. Now, when you measure a specific set of these properties, you establish a state. It's basically a mathematical snapshot of the system's condition at that exact moment. Consider a system undergoing zero spontaneous change, like a stabilized piston cylinder. It has achieved a beautifully balanced state called thermodynamic equilibrium. It's perfectly maintaining a stable balance thermally, mechanically, and chemically. And finally, Section 5, Types of Processes. A process is really just the actual move that happens when a system mathematically shifts from one of those equilibrium states to another. To track these moves, engineers use the prefix iso, which literally just means same, or holding a specific physical property constant. So an isobaric process holds pressure exactly the same. Isothermal holds temperature constant, and isochoric keeps the specific volume constant. It's just a really elegant way to simplify some incredibly complex energy calculations. There are a few other critical moves in the rulebook you should definitely know. An adiabatic process is fascinating because it means there is absolutely zero heat transfer into or out of the system. The boundary is acting like a perfect, flawless insulator. Then there's an isentropic process, where entropy remains constant. We also broadly classify these processes as either reversible, meaning they can be perfectly undone without leaving a single trace on the system or the surroundings, or irreversible, which, is a lot like dropping and shattering your favorite coffee mug. It simply cannot be magically undone. So, what's the big takeaway here? Why does all of this matter to us? Well, it's because mastering this exact thermodynamic rulebook is what allows technologists to build what we call steady flow devices. I'm talking about massive turbines, heavy-duty pumps, and industrial compressors. These devices operate for long, continuous periods under these exact steady conditions. They are literally seamlessly turning theoretical physics equations into the real-world power that lights up our homes and drives the entire economy forward. And honestly, seeing this brilliant application of fundamental rules leaves us with a pretty inspiring thought. Think about it. Every single major leap in modern engineering has come from a deeper understanding of these exact thermodynamic states and processes. So, as we continue to push the absolute limits of technology today, as we expand into quantum realms and deep space exploration, you have to wonder what undiscovered energy transformations are just out there waiting to be harnessed next.